Hi, we're back again, and I'm moving on now to some more parts of the sensory memory system. We're talking about iconic memory now. It is a very, very fast, momentary sensory memory of visual stimuli, a photographic or picture image memory lasting no more than a few tenths of a second. Okay, that's a lot faster than a second. Um, you can register the exact representation of a scene momentarily. It doesn't mean you're going to remember all the details of it. It's in and it's out. It's for you to react very, very quickly to situations, I guess you could say, it's somewhat life and death. But think about in a non-life and death situation when a quarterback throws a football downfield. A receiver who's being guarded by another player might have hands in his face, is running and looks up and then sees the ball, and then looks down, then looks up. And what's going on is the person trying to get the ball, receive the ball, can place where the ball is in space very, very particularly and put their hands in a position that will allow them to catch it appropriately. And that can only be done with iconic memory. You can't hear the ball. You're not doing it with your ears. You're doing it with sight. But that doesn't mean that once a person catches the ball, they're going to have a memory of, I knew where it was all the time, and I can tell you exactly what, whether there were laces facing me or not facing me type of thing. All that detail is going to go very quickly. All right. Echoic memory is momentary sensory memory of auditory stimuli. So it's the ear, okay? So if your attention is elsewhere, sounds and words can still be recalled within 3 or 4 seconds. So even if you're not sort of paying full attention, if I were to suddenly say, Susie, what did I just say? And let's say you weren't paying so much attention, you might be able to get a couple of words at the end of my sentence there. That's echoic memory, okay? All right, now what we have coming up next is a guy named Sperling. And he did these studies. And I'm going to actually do I have a way to show you a little bit of the study in class, so remind me. But it doesn't work right now with the way I have the computer set up. It won't work in this format. So I'm just going to talk about it instead of showing it to you. But we'll do it in class for real. So here you go. You got Sperling, and basically he showed people, started off with a blank screen. So he started off with this. And then very quickly, within a 1/20th of a second, he would flash these letters on the screen and ask people to repeat what they could remember. And the question was, for Sperling, was, what do we remember? Did we take in all 9 letters, or did we only take in a certain number of them? Are we limited? And for a long time, it was thought that we could only take in so much. But in reality, what Sperling showed with this experiment was, yes, indeed, we took in all 9 letters, but we're not able to say them all, and here's why. So he presented a matrix of letters for 1/20th of a second. Report as many letters as possible once they flash. Subjects recall only half the letters. Was this because subjects didn't have enough time to view the entire matrix? No. And now how did he figure this out? Okay, so that people can see and recall all the letters momentarily. Sounded low, medium, or high tones immediately after the matrix disappeared. So the tone would signal which row to report for each person. Okay, when he did it this way, the recall was almost perfect. So basically, let's see, where is this? Right here. So here, you were to report a certain row based on the sound that you heard right after it flashed. So it would go boop, boop, and then you would hear boop, boop, beep. I don't know if that's good or not, but then you had to report what you heard. And of course, you didn't know which tone you were going to hear. And what he found was people could always report based on the tone that they heard. So he found that basically his conclusion was this: if you hear the high tone, which I'm pointing at here, which you can't see me, I'm pointing at it like you can see me. If right here, if you are told to report the high tone, you'll start saying KZR. While you're doing that, in the process of doing that, your memory for all the other letters is so short that you forget those other letters while you're saying you're reporting the letters that you were told to report based on the tone. So literally, you see all 9, and you could report any one of the 3 rows when immediately requested to do it. But while you do it, you'll forget the other 2 rows. Pretty cool stuff. Okay. All right. And what did he have here then? So memory for the image fades after about 1/3 of a second or so, making report of entire display hard to do. So that's what I have there. All right, storage, short-term memory. So short-term memory, you are limited in duration and capacity to a magical number of about 7 items in your short-term memory at any one time. 7 items, plus or minus 2, depending on any individual's ability. Okay, so what does that mean? Okay. Okay, so now we're going to talk about, we did sensory storage, short-term memory storage. Now we're going to look at long-term memory storage. Carl Ashley is the man here who gets the credit for having sort of the most insightful study back in 1950. What he did is he trained rats to solve a maze. Nothing unusual there. Then he cut out pieces of their cortex and retested their memory of the maze. And how many rats and how many times to do that? I think he did this in the thousands. He was not doing this with just one and checking it out. He was trying to find where is long-term memory stored. So his idea is if he taught them the maze, that maze should be in their long-term memory. They should understand it and keep the speed at which they can zip through the maze once they've learned it the same if he is only taken a part of the brain out that has nothing to do with long-term memory. What he found is no matter what part of the brain he took out, the rats always remembered some part of the maze. Okay, they never completely forgot the maze, but at times they never completely remembered the maze. So interesting. And so basically his conclusion was, and I'm just looking on some things here. Memories don't reside in a single spot in the brain. I guess you could almost say that long-term memories seem to reside almost in the electricity of the mind. Okay, the fact that the brain is on. We have not been able to verify one place or the other where exactly long-term memory resides. There are some places in the brain that, yes, when damaged, we do know you'll lose certain parts of your memory. But when it comes to most of your long-term memories, they're all over the place. So that's that. Long-term potentiation. Okay, this is an increase in synapses firing potential after brief rapid stimulation. So basically, you could put it. Let's see. Let me see if I can say it better. In experiments rapidly stimulating certain memory circuit connections has increased their sensitivity for hours or even weeks to come. So when they were actually trying to increase someone's sensitivity to remembering things with long-term potentiation, okay, it can work for hours or weeks. This prolonged strengthening of potential neural firing is called long-term potentiation. It provides neural basis. So we're looking for a neural base. Now we're actually looking at the biology, okay? It provides a neural basis for learning and remembering associations. Mice that lack long-term potentiation seem to have trouble learning, while drugs that enhance LTP, or long-term potentiation, increases learning. So we can actually shoot drugs into rats, okay? A blow to the head or even drinking can disrupt short-term memory from being transferred to long-term memory, and therefore it is forgotten, okay? So like a concussion, boom. In the last few moments of a football player's on a play, and a football player gets a concussion, they have a tendency to not remember the play at all, because the play, those few moments beforehand hadn't been laid down into long-term memory yet. Boom, a blow to the head disrupts that process, and they can't do it, okay?